Hi, welcome back to the Sunday doubt solving sessions. Today we'll be discussing about whatever happened in week 6, which is mostly discussions on the modified governing equation for the wave equation and also the dispersive and diffusive terms. What do they mean and what implications does it have on the equation and the solution? So the week's discussion was mostly based on the wave equation as discussed, and the how the wave equation operates is that it transports the solution from one point to the other without distorting it at all. So that is how an ideal wave equation solution looks like. Can anyone tell me what type of partial differential equation the wave equation is? Is it parabolic? Is it hyperbolic? Is it elliptic? I'll wait for your answers in the chat box. Great, thanks Dipesh. It's hyperbolic. And for hyperbolic equations, we had some preliminary discussions regarding this in the earlier sessions and also in the course beforehand, where we had seen that the hyperbolic equations are propagative in nature, just like the wave equation. If you recall, then we had a discussion on how the behavior of an ink which you have poured into a river would look like. Like if I'm just, if there is a river and a person goes and throws a bunch of ink in the river at this point, so then it just gets propagated to another point. So this is an example of wave equation. Here the major mechanism of the transport of the ink or say any property is because of convection. So the wave equation is basically a convection driven equation as opposed to the so yeah, so the wave equation is the convection focused mechanism of transport of a property as opposed to the diffusion type of equation. Can you tell me what type of equation is a diffusion equation? For if you recall, we had discussed about if there is a still water and then you pour a drop of ink over here, then it will spread throughout the trough of water, whatever still water there is. So what kind of governing equation governs this transport behavior? Once again, the question is regarding if it is hyperbolic, parabolic, or elliptic. Okay, I'm sure you recall, but this type of equation was elliptic. No, Lenish, that was this type of equation where I'm talking about a diffusion based equation. Basically, when you put a drop of ink in still water, like in a tray of still water, then how does it propagate? Then it propagates through diffusion, and diffusion is governed by an elliptic equation. The hyperbolic equations is what was discussed in the classes throughout the week. And an example of the hyperbolic equation would be that if you throw some ink in a river and then you say that, okay, this is my ink. So then how will it propagate? Then it will propagate because of convection. It is a convection driven process, and convection driven processes are hyperbolic. Okay. So wherever you have diffusion driven processes, those are typically elliptic or parabolic depending on the time dependency. As we had discussed earlier, that Laplace equation looks something like this, and this is the form of a steady state heat equation. I'm pretty sure we all remember. Um, and if you have something on the like if you have a time dependency of this function phi on the right hand side, then it's a parabolic equation. So this was discussed in the earlier classes. Anyway, this is just a brief sort of revision at the types of equations, because we need to continuously keep in track what we are trying to achieve by studying all of this. So one of the major things that I would like to once again bring up in classes, that please always have a perspective of why we are doing what we are doing. Otherwise, this is a lot of math, of course, but we need to remember what we are trying to achieve by doing this math. Because our objective is to finally be able to make solvers based on the CFD solvers based on these governing equations that we are discussing. If you want more inputs regarding that, then I would be more than happy to take a class on that as well. Anyway, so I'll come back to the topic at hand. But once again, just for your knowledge, in case you want to pursue CFD development, then like we can totally discuss on that, but it will have to be in class because during the week I'm a bit busy with other things. Okay, coming back to topic at hand. So we're talking about modified governing equations. Okay, so modified governing equation is something that we had discussed with regards to the heat equation as well, where we had said that when we have a governing equation which looks something like this, du by dt equals to, I'm going to write the heat equation right now, one dimensional heat equation. If we have something that looks like this, then how do we numerically represent it? We numerically represent it by using our Taylor series derivatives, and then we get some derivative value over here which looks like un plus 1 minus un at I where by delta t is equals to alpha this expression is for the central differencing. For example, if I write the central differencing example, then 2in plus ui minus 1 n. So we had discussed this in the earlier classes in the previous weeks. So then basically what are we doing over here? We are trying to find our derivatives in terms of certain knowns. And then when we do that, when we strive to do that, what we are implicitly adding is some error. Okay. So error of whatever, error of order, some order of delta x and some order of delta t. So over here, the order of delta x is this, and of our delta t is what? Anyway, so you understand what we're trying to do from here. That is our original governing equation, physical governing equation. We make a numerical governing equation, which is essentially a modified governing equation, right? So, of course, when we are making all of these mathematical manipulations, we are definitely affecting the behavior of the mathematics and also the physics. Why? Because we said that our physics is governed by this equation. Now, by doing all of these approximations, we're essentially adding or subtracting some terms which we're calling the error from the physical governing equation. So this error is something that creeps up in the physics. Okay, because you're basically just changing. You are telling the solver, or you're telling the computer program that your physics behaves like this, like whatever I have written, this thing. So therefore, that behavior is implicitly different than your original governing equation. But we hope and we wish that this difference in the behavior is not very acute. Okay, just erase this so that notes don't get cluttered. And right. So then our hyperbolic equations, which we have discussed in the class throughout this week with the professor. So what that does is that it takes the solution and it transports it in space with time and does not distort the solution. That is what an ideal governing equation, that a hyperbolic wave equation does. Okay. But however, due to numerical approximations, the governing equation has additional terms that may affect the evolution of solution in time. That is exactly what we just discussed. So then the modified governing equation is written as this form. So this form is important for you to remember, because why we talk so much about standard forms in these classes is because standard forms allow us to have a simple way of comparing two different cases or any case and describe its behavior based on known behaviors. Our entire objective with doing physics as well is to approximate behaviors as something that we already know. So therefore, this what do you call it? This form of modified equation is what we need to remember. That is basically this is your actual governing equation. This is the approximation to your actual governing equation. Okay. Essentially, if it was like the true governing equation, what you would have written, you would have written a minus ux. This is for the hyperbolic once again, equals to 0. Now, since this 0 is not true anymore because we have modified the equation, so a truncation error comes. So we write our equations in a way that it mirrors the true governing equation. Okay, this is how you would write. Let me write it down. This is how you write your physical governing equation. Okay, before I proceed, I'm sure you must have attended the lecture by Professor Arnab Rao, which was a live lecture. If you haven't, then also not an issue. It's on YouTube. Um, Sorry, it's on your NPTEL drive or whatever. So in that, I had requested the professor to discuss about ADI. Akshat, I think you had a problem with that, if I remember correctly. How to divide a pentadiagonal system into two tridiagonal systems. Hopefully, he has addressed that, and that is something that has been clarified. Okay, so now moving on. So, if a modified governing equation um, has extra, sorry, has extra even derivatives. That is, this is what my actual governing equation looks like. If my truncation error is going to have some even derivatives, okay, even derivatives, that is the second derivative or the third derivative of the property u, or odd derivatives. Okay, right. So if it has some even derivatives, then let's read what's given. The amplitude and the amplitude growth or decay is affected. So basically terms that look like this in my modified governing equation, d4u, d6u, any terms in my governing equation that look something like this are basically telling me that my solution's growth or decay behavior is affected. Okay, so we would like to recall this again. Once again, I'm bringing in the diffusion example. So, do you understand what I mean by when I say that amplitude decay or growth is affected? So, why that is affected is because these terms, that is the even derivative terms, their behavior is diffusive in nature. Just like I spoke about the ink that gets diffused in still water. So, essentially, its action is averaging. When you sit and you break down your even derivatives in terms of your numerical approximations, you will find out that each of these derivatives are basically what they're trying to achieve, that these even derivatives is to sort of spread the solution around, it's to smooth the solution or to diffuse it, basically average it. So it just takes solution, like we had talked about that earlier, when we have some grid point like this is the central point and then it has four neighbors. So essentially, when we have a diffuse this kind of a even derivative term, what that does is it tries to pull the solution from all of these 4 points and give it to this central node. So what it's doing is it's averaging. So what this does is that if you are going to have a second derivative term, it's going to keep on continue to basically smooth out your solution. That is, if it has a like, it can also have the opposite effect, that it keeps on like there's an error, it keeps on increasing it. On a this also you can understand from the simple perspective that if your all your answers on these 4 points are wrong, then if you keep on supplying that wrong answer to the central node, what you're going to eventually end up with is like a completely wrong solution. That is, the amplitude goes out of bounds and it just it just blows up. Okay, so we don't want a solution that blows up the errors. Obviously, we wanted something that will decay the errors. So then these terms, that is the even derivative terms, can have either the effect of exponentially growing the error, or it's going to have an effect in exponentially decreasing the error. So, which is what is called dissipation. That is, you dissipate the error, right? Okay, so and this is about the even terms. For the odd terms, what the odd terms do is that they essentially change the speed at which this solution propagates. That is, if we come back to this diagram, what the odd terms are going to do is that they're going to somehow alter the speed. I don't want, this is just a demonstrative thing that I'm saying, that since this is like the slope at which they're moving, right? This thing that I've made right over here. So instead, maybe the odd solutions will cause my solution to move yeah, along this direction. Okay, maybe not such so acute, but essentially it changes the speed. Okay, in magnitude or in direction, mostly magnitude, but also in direction based on the wave number. So both of these wave number of the whatever you're dealing with, whatever wave you're dealing with. So basically, what I mean to say that if you have a solution that looks like this and then a solution that looks like this, both of those are going to have different behaviors when subjected to the same modified equation because of their wave number. Okay, we'll see what that means. If you've gone through the lectures, you would have seen that basically we had broken down our whatever these extra terms in the governing equation are in terms of the e raised to the power something something, etc., over here. So from that, the conclusion was that the even terms are going to affect the amplitude. Meanwhile, the odd terms are going to affect the speed at which this moves. So both of these effects are tied to the wave number, and depending on the wave number, that is what I showed right over here in this diagram, your reaction to the same terms in the equation are going to be different. Okay, hopefully that was clear. um,
Ma'am, can I ask a question?
yeah, sure, Ms. Shipra.
Ma'am, this conclusion can be done seeing the coefficient of even order derivative and odd order derivative by by mm, by its by depicting the physical problem.
Okay,
Means
so
how conclusion can be done physically, it's happening due to the presence of this odd order derivative and even order derivative.
yes, so you're asking how can we physically prove that this is happening.
Yes.
Okay, so this is something that was also addressed in the class. Anyway, I'll just sort of try to quickly give you an example. So basically, if we have over here something like du by dt minus, let me just write it in terms of ut, something like this, ut minus a ux, so that it's similar to whatever you've done in class. That's why I'm trying to write it in this form. Um, is equal to some truncation error. Okay, so then let's say that we have a term uxx, and let's say we have a term which is u. Okay, fine. I'm just going to put a plus over here. Uh, so let's see when we expand this, what happens. So then you remember we had spoken about how you can write down different things. Essentially, you'll have to open this up. Okay, Shipra, I really advise you go through the thing because I have not I haven't gotten it written anywhere. But essentially, what happens is that when you break down this uxx, okay, so you're going to, okay, let me do it. Wait a second.
Okay, okay.
It's okay. I'll take some time, but if you want me to explain it, then basically you're going to get something in terms of cos theta, okay? Because you're going to write it as this. Fine. Whatever terms you get, you're going to write them in this form. Basically, open this up, okay? So how will you open it
Mm.
up? If you want to use central differencing, then you will open it up as I plus 1 minus 2 ui plus ui minus 1 divided by 2 delta x. That's how you would open it up. Then you would write this ui plus 1 as un I theta into k theta or whatever, theta, let's just say theta, into I plus 1. And you're going to write this as minus 2 into u I theta I into I. Okay. So basically, you're going to write the other term also like this. But then what you're going to do is that you're going to take out all the common things. That is this thing, u I theta into I. Okay. So you're going to be left with E minus theta minus 2 minus plus EI theta. Sorry, EA minus theta. Right? So then you're going to break it up into cos x, cos theta plus sin theta minus 2 plus cos theta minus sin theta. Okay, I hope I'm not going too fast. This is simply breaking down this EI theta into the polar form of representation, and then you cross it off. So basically you're left with just cos theta. Okay, so cos theta is not multiplied with iota. Over here iota is also going to be multiplied. Whatever terms are multiplied with iota affect the speed. Okay, why? Because that
Mm.
comes into the sine part of the equation. So basically if there was a negative over here as well, then I would have gotten something in terms of sine theta which would have iota multiplied with it, but I don't have that. Okay, so whenever I have that, that goes and multiplies itself with the where the velocity is multiplied. You know what, Chipra? I'll derive this and I'll send it to you because I think I'm going off on a tangent. It's in, I think, one of the last classes. But basically, what happens is that whenever you're breaking this, your entire equation up into various halves, this coefficient you are going to alter because of whatever you have over here. Wherever A is coming up, when you completely break this down, you're going to find that something is added with A plus something into whatever you have over here, and you'll realize that this is the modified speed. So this happens only for the odd derivatives.
Okay.
I'll get back on that. Please write me a mail on this. I'll get back on it. Okay.
Okay. Okay.
Um, this is all given in the lecture. I hope I have not confused you all, but I'll move on with whatever I have planned. Right. Basically, Shipra, you just need to break it down in terms of whatever you have already learned in class. Okay, it's not going to be difficult, and you're going to be able to see that wherever your A comes in, you're going to be editing the A in a way. Okay. Anyway, so basically, the effects of the derivatives, as we've spoken about it, are as I just told you. Right. Then there is another, like whenever we are basically applying a numerical scheme on a particular governing equation, so that you can't apply every scheme over every governing equation. Okay. Why is that? It's because we are going to add some truncation error that we saw over here, right? So whatever this truncation error is, it should not drastically alter my governing equation such that I cannot get any meaningful result. Okay, if I cannot get a meaningful result, then there is no point in me doing a numerical analysis or even attempting that problem. Okay, so then I should have certain tests to see whether I can apply a particular numerical scheme for a particular governing equation or not. So number one, I've written at number two, but I'm going to talk about stability first. So stability is something that we have been looking at since the past 2 weeks, where we have something known as the von Neumann stability criteria, which operates in whatever way I was just telling Shipra about the how you break down the derivatives in terms of e raised to power I theta and try to sort of get a relation for the ratios of un plus 1 by un. Okay, and you want this ratio to be less than 1. Why do I want this to be less than 1? Because whatever the ratios of these amplitudes are, those are analogous to the ratio to the ratios of the error. So numerical behavior of the error, decay or growth is the same as the numerical behavior of the amplitude growth or decay. Okay. So this is something that we do, which we use the von Neumann stability criteria. So then in von Neumann stability criteria, we're trying to achieve this. And if we are able to, and this is fairly easy to do, we can prove whether or not a scheme is stable by simply looking at this ratio and making our conclusions. So this is number one. Number two is consistency. So what is consistency? So if you have a modified governing equation, which we've just spoken about, then you don't want that equation to have a totally different behavior. You want, of course, it will have some difference in behavior, But what your objective is, that when you are taking delta x and delta t approaching 0 in an ideal condition, okay, where you have no numerical around, like no machine generated errors or any other errors, okay. So then if you have delta x comma delta t when they are approaching to 0, you should be able to get your original governing equation back. Okay, what that essentially means is that all of your terms over here, whatever you're getting in truncation error, they should have a factor of delta t or delta x. Okay, like they should be multiplied by either of the terms. Why? Because when it will contain, when delta x and delta t will tend to 0, that time what will happen is that these terms will go away, and when they go away, I'm going to get my original governing equation back. Okay, because my truncation error will be 0. Is that fine? So that's known as consistency. And if a numerical solution is approaching the real solution, okay, like whatever your actual solution you're supposed to get from that physical problem, if a numerical solution is approaching that, then it is called convergent. And one theorem, Piri-Lax theorem, states that if a scheme is consistent and stable, it is convergent. So from this discussion and whatever we have been discussing over the past few weeks, we know that it's easy to prove whether our scheme is stable or not. Okay, we are able to define some range of values for D in terms of the steady state heat equation, or the CFL, or current of Frederick Lowry number, CFL, that we have for the wave equation, such that we are able to say that, okay, in this range, this scheme is stable. So that discussion we have had in the last class as well. Right. So we're able to prove it's stable fairly easily. We're able to prove it's consistent fairly easily. So then how we evaluate a scheme is that we just try to find out whether it's consistent and stable, and then we say it's going to be convergent, and therefore it serves my purpose. Okay. So this is the background on that. If we have time, then we will be addressing Shipra's question in detail at the end of the class. Okay. So fine, we're going to be jumping to some questions now. What is the formula for dissipation error after fifth time step if initial amplitude is A naught? So what do you think? Dissipation error would be A naught minus AN. Okay. And AN plus 1 for any n divided by AN is equal to G. So I need an answer in the chat box. Very easy. It's important to remember it's the fifth time step. Okay, great. B. Thank you, everyone. Yeah, that's B. That's the right answer. Okay. Okay. Next question is, what is the truncation error for first order linear wave equation? Let's write down the first order linear wave equation first. Ut minus A. A is the wave propagation speed. Ux is equal to 0. This is my actual equation. Okay. It's asking me what is the truncation error for first order linear wave equation solved using forward time central space scheme if A is less than 0. Okay. So first let's see what my forward time central space means. That means basically that I'm going to have, let me just use the blue pen, un plus 1 minus un at I goes to delta t, this is forward time, minus A into, what is it asking me? Central space. So central space is again ui plus 1 at n minus ui at n, sorry, 2 into ui plus minus n, sorry, plus ui minus 1 into at n by 2 delta x. Okay, So this is my equation. Now I need to find out what is on the right hand side, which is that I need to find the truncation error. Then what will I invoke? I will invoke my Taylor series. Okay. So in Taylor series, what had I learned for the time part of the things? Let me just write time so that we don't get confused. Time is equals to uin plus delta t into ut plus delta t square by 2 factorial, then utt plus delta t cube by 3 factorial plus u triple t, and so on and so forth. Okay, agreed? Everyone agrees with me on this? Okay. So then from here, what truncation error am I getting? Let me just try to recreate whatever I have over here. I'm just going to implies. So here what is left with me? Okay, ut. This is what I need. This is what I'm trying to replace by this. Plus I have some truncation error. What is my truncation error? My truncation error is delta t. Oh, it's not delta t at all. Huh, no, it is right. It is delta t by 2 factorial. Why? Because delta t is going to be divided throughout, right? U double t plus delta t square by 3 factorial u triple t. Okay, so I have my error terms for time. Let me see where these error terms of time are, uh, like where am I getting the same error terms. Basically what I did is that I replaced this ut over here with this thing, and therefore I'm going to have all of this as truncation error on the other side. So either I'm getting the option A or B. Those are the two options that are matching with whatever I have just done. Okay, then let's do the same operation for the space. So once again, we're trying to reconstruct what we have. Ui plus 1n is equal to what? Ui at n plus delta x ux plus delta x square by 2 factorial u double x plus delta x cube by 3 factorial u triple x, and so on and so forth, right? And I have also ui minus 1 is equals to ui n minus delta x ux plus delta x square by 2 factorial u double x plus delta x cube by 3 factorial, sorry, not plus, minus over here, u triple x plus 1 and so forth. And then what did I do to get my central differencing? I just simply added these both. Adding now I have gotten my expression, whatever I have on the right hand side, sorry, whatever I have in the numerically approximated equation that I had written earlier. So what is my truncation error? What is my truncation error? I have delta x, no more square, 2 factorial uxx plus I have, okay, so the odd terms have been cancelled out, right? Oh no, but then I don't want that, right? Okay, so then I don't add these, I subtract these. Yes, I have made a mistake. So we subtract. So when we subtract, only then we want to preserve these terms. We want these terms in our like we need to recreate ux. So I can't just cancel it out. That would like defeat my entire purpose. So now over here, this delta, this term, the even terms get cancelled out. So I have over here delta x square into u triple x, right? But this is accompanied by a 6 factorial. This is the first term. The second term of error that I would get is analogously, okay, I haven't written it down, but analogously this would be uh, what would it be? 5, right? So then 4 by 5 factorial, sorry, 3 factorial to ux. Anyway, this is a very small term, so I'm just going to ignore it. I don't care about this. So basically, this is what my spatial error should look like. Therefore, error is equal to, in my calculation, I hope you guys have also been following this side by side. So in case you disagree with me, please speak out. Okay. U triple T. Three factorial U triple X. Let's see what matches with this. So this matches with my. Do I have a negative sign anywhere? No, I don't. Yes. Then this matches with whatever I have over here. That is A. Option A. Option A is my correct answer for this. Right. Okay. Then moving on to the next question, which is that clear? Was it okay? Was that okay, or did I make a mistake anywhere? In case you've been following along. All right. I have a feeling I've made a mistake somewhere. So in case you have spotted it, then please let me know. FTCS is fine. FTCS is fine. Anyway, okay. And move on. So now we have the FTFS scheme. So this is going to be Alfrina, you have something to say? Just unmute yourself and talk to me. Right. So I'm going to move on. Of course, any time, just feel free to unmute yourself and speak. If I have a mistake in this, then please let me know later on. Anyway, I'm going to move on with the next question because we're short on time. So this is FTFS scheme. So we know what the FTFS scheme looks like. Let's have a look at what FTFS means. FTFS is forward time, forward space. So forward time, forward space scheme looks like let's just write down the equation because they've asked us for the linear wave equation once again. That is ut minus a u ux equals to 0. FTFS is forward time. So once again, same treatment with time. Delta t is minus a into, and ux is going to be forward space, right? That is fi at n minus dy minus n. Agreed on this? This is what the forward space looks like. So what you will do is that once again you will invoke your Taylor series, and you're going to try to find out what the answer should be for the error. So what I have written over here is that this is the right answer. So just confirm it. So basically the operation that you have to do is that you have to just invoke your Taylor series, see what's on the right hand side, plug it in over here, and that whatever you get over there is the truncation error. Okay, you see over here also we are given something like this. This is like the RHS, which was supposed to be 0. Anyway, there are a lot of very similar questions. And I think that's the repetition. Oh, Please give me a moment. I'll just like, I'm just taking out some new questions. Just a second. Please give me 2 minutes. If you want to have any discussion amongst yourself, please feel free to do so right now. Also, has anyone developed the sort of a solver on anything yet? There was some interest regarding the Gauss and Jacobi solver earlier. That's why I'm asking this question. Can you see my screen now? No. Okay. Okay. Thank you for waiting. There was some hold up from the questions. Okay. So now we have a sort of a practical question on CFL, that is the Courant Friedrich Lorentz number, and basically that is a stability criteria for the wave equation. So what are requirement from all times from the CFL is that the CFL should be between 0 to 1. Sorry. Okay, so here we have a question which is based on that. What is the limiting wave speed which restricts the numerical solution from becoming unstable unbounded if delta x, we're given the delta x and the delta t, right? So then the definition of CFL is basically a delta x by delta t. Okay, so then you need your CFL to be basically you need an a such that your delta x over here is 0.0125 whole by 1.5 into 10 raised to the power minus 5 should always be less than 1. So can you quickly solve this for me and tell me the value of A? I'm waiting for the value of A on the chat box. Meanwhile, I'll just get a few more questions. Dx is 0.0. Wait a second, I'll just share screen once again. This is my dx is 1.5 into 10 to the power minus 5, and delta x is 0.0125. Please solve this in the chat and write the answer in the chat box. I'm waiting. The CFL indicates the stability criteria. Sorry. You will also encounter this when you are going to be using ANSYS Fluent, in case you are planning on doing your CFD studies using that, by the name of underlaxation factor. Okay. Also, we have studied something about underlaxation factor in our PSOR and etc. schemes. Basically, it's just sort of causing your solution to move more slowly than otherwise. Right, so the answer for this is 833.33 meter per second. Please answer in the chat box. This was a fairly easy computation. So 0.012? I'm sorry. No, this is 10 to the power minus 5, Alfrina. Why are we not getting the correct answer for this? We want the answer for A, the limiting value for A. That's really surprising. 1.5 into 10 raised to the power minus 5, right? So did you not raise it to the power of minus 5? That goes and becomes plus 5 on the other side, right? Wait a second. I do have the answer for this over here, which I have computed. Oh, I am sorry. I have misdefined the CFL in here. Just this. Sorry. That's a fault on my part. I miswrote. Yeah, thank you, Dipesh. That is the right answer. No, C equals to A into dt by not dx square. It's only delta x. There's no square over there. It's fine. So right, the answer should be 833.33 meter per second. I'm sorry, I miswrote the definition of CFL over here, but you should have corrected me on that. So please keep in mind that you have to keep on attending the lectures, like going through the video lectures that the professor is giving. So this is the CFL, and the objective behind the CFL, like what the CFL basically tries to tell you, is that your rate at which information travels should match up with the what do you call it? Um, right. The rate at which information travels numerically as well as physically should be consistent. They should be comparable to each other. And under any case, the numerical rate of information travel should be slower than the physical rate. Okay, this is hopefully now after the correct definition, we would have gotten the correct answer, which is 833.33 meter per second. So if we have a speed of sound or speed of wave propagation above this, then we are not going to get the right answer. For like then our solution is going to be unstable. The CFL will not be within 0 to 1. I'm sorry for that. Okay. Next we have over here, if the coefficient of uxx, hopefully this was clear. I'm sorry, I just messed up in this respect. Uh, Hopefully that's not too much confusion, but this is the CFL. Please go through the definition of this. This is a very important term. This is a very important number. Okay. Definition of CFL. Essentially, this is like one of the criteria that you will be using again and again, whether you're using a commercial software or you're designing a software on your own. Stability criterion. You essentially what happens really is that you have a delta x already, which you have from your mesh. You have an a, you cannot change the a because it's the speed of sound in terms of like if you're looking at gas propagation, speed of sound. And then you basically need to decide a delta t. So you decide a delta t by multiplying it with a certain CFL such that the CFL is always less than 1 or whatever. You just keep on stating the value for CFL. Anyway, if the coefficient of uxx for of a modified PD form of linear advection equation, what is a linear advection equation? Can anyone tell me? It's just the wave equation. It's the linear wave equation. What we mean by the linear wave equation can also be called, so what is advection? Advection is essentially convection. Basically, advection convection are mostly used synonymously with a coefficient constant in convective term. Yes, yes, you're right. No linear advection equation. Okay, the coefficient of uxx in a modified PD form for linear advection equation is this term. There is a negative value. Negative value. How will the time march solution proceed? It will produce negative numerical dissipation. It will be numerically stable. It will be numerically unstable. And option D, it will be numerical. It will produce anti-dissipation. So do you agree with one? If you have a negative coefficient for uxx, will it produce a negative numerical dissipation? Yes, it will. Okay. It will provide a negative numerical dissipation. We talked about how second order terms, that is this kind of a term, provides a dissipative effect, right? So when it is accompanied by a negative coefficient, you will see that it will have a negative numerical dissipation. That is, it will basically amplify the solution. Does that mean that it is clearly not numerically stable? It is numerically unstable by all definitions. Numerically, it will be numerically unstable, and this kind of a behavior is also called anti-dissipation. So it will produce anti-dissipation. Okay, so this is what happens. Um, if you want more clarity on that, just have a look at whatever we did in this first question, right? Basically, just go through this and see what effect each of these terms are having. When we are having this sort of a like, the best way to look at it is by what I spoke about earlier, this sort of a diagram. So you keep this in mind because it might be confusing, like how and why are we anyway, cannot draw circling distance anyway. So basic, It is anti-dissipation. Yes, it is anti-dissipation. It is a sort of anti-dissipation. It's also called anti-dissipation. There are three options. The three options are correct. A, C, D. These are right options. Is this how it's called? Anti-dissipation, negative dissipation. These are just the terms by what it's called. Okay. Anyway. Okay. So the next question is based on a sort of visual inspection of what each of these terms do. The figure below shows a comparison between an analytical and a numerical solution of a linearly advecting step waveform. So basically this is your step waveform and it is just advecting that it is just keep on moving in space and time. Okay, what are the types of error present in the numerical solution? So my exact solution looks something like this because it's a step waveform which is moving in time. Okay, but then when I'm basically numerically solving it, I'm getting something like this. So what all types of error are present? Ah, oh, this is an important feature too. So let's see what is present. So we can see there is some sort of smoothing effect over here, right? These sharp edges are now smoothened. So which terms have we been continuously been talking about their dissipative or their smoothing? Those are the second derivative terms. This figure is telling me that there are some second derivative terms present because you see that although my real solution has sharp corners, my numerical solution does not have them. So that immediately tells me that there is a dissipation. Okay. Okay, dissipation, there's diffusion as well, because again, same thing that when you have a dissipative effect, I'm sorry, I did not understand what do we mean by rimple? Okay, and dispersion is when there is a change in the speed of transport. Okay, the patient is right. It's all of the above. Essentially, this is the correct answer. Basically, there is a diffusive effect, there is a dissipative effect. Dissipative and diffusive effects commonly go hand in hand because they're governed by the same numerical term. And dispersion is there because we're able to see that there is some disparity in the sort of speed that is being seen in the for different waveforms. Here there is some distortion in your waveform which is telling me that okay, this is sort of transporting along this line. So therefore whenever you see these kind of wiggles, those might very realistically be an indicator of dispersion. And dissipation and all you're able to see because all of your sharp edges are being are being smoothened out into smooth edges, right? Hmm. Okay, then define modified speed for the equation given below. Du by dt plus 825 du by dx. So what is this 825? This 825 is my a is equal to, this is the coefficient for the fifth derivative. So since we have the fifth derivative, that is the odd derivative, we know that basically what is happening is that your speed of propagation is going to be affected. Okay, because we spoke about how the odd derivatives are dispersive in nature. Okay, that is the change in the speed at which the solution is progressing. Hmm. More than the speed at which the solution is propagating, not progressing, propagating. Okay. So first we'll just see what is happening over here. Solution will linearly grow, exponentially grow. Mm, I don't think these are the right options in this case. But since there is no exponential term, that is, there is no second derivative of the or fourth derivative or sixth derivative, we know that there is no exponential term associated with this. There is no exponential growth, there is no exponential decay, because there is no even terms that are there, even derivative terms. So actually the solution will simply propagate. That is what my take on this is. But the speed of propagation will be different. I'll check this out. But speed of propagation will be different. Now what will that speed of propagation be? This is something that has been derived in class. Shipwright will answer your question as well. That essentially when you open up your whole terms with how we have discussed earlier, just a second, how we have discussed earlier. So then basically your speed will be impacted by this fifth derivative term as follows: a plus k4 into this coefficient, This for the variation in speed due to fifth term. Okay, so a over here I could see is 825 plus 10 raised to the power, k is 10, so 10 raised to the power 4 into 12.5 into 10 raised to the power minus 4. The simple, this is just 8, what is this, 837.5 meter per second is the modified speed. Okay, similarly if there was, for example, a third derivative term, then you would get something like into coefficient variation due to third. Yeah, options should be numerical value. You're right, Dipesh. This is some strange thing over here. Just ignore the maybe the error in the question. We just ignore this. But essentially, we are able to understand that you're not going to be having any exponential behavior, because we don't have the terms that bring in the exponential behavior. Speed due to third derivative. Okay, so then also in these classes there was some discussion regarding two schemes. One was the leapfrog scheme, and the other name I'm not able to recall. I think it's something lax or something related to lax something. But then essentially, like when you go through those schemes, rather than focusing on the names and what the names are going to signify, just look at what basically the scheme is doing. The leapfrog scheme is such that it takes two, like it sort of operates on two time steps at one time and something of that nature. So just instead of trying to look at it from a very mathematical perspective, look at it from a physical perspective, that what is it going to do to your solution. Anyway, right. So that's all I have for today. Shipra, please write to me. I'll write that derivation and I'm going to send it to you in case you need it. If Alfrina, you had spoken about developing solvers long back, I think 3-4 classes back. If you want to discuss that, please stay back on the call. The rest of you can leave. Thank you.
Okay, I will mail you, ma'am.
Yeah, sure, Shipra. Okay. Thank you for your time and attention today. Thank you.
Thank you, ma'am.